Hello, welcome to our smart supermarket. The aim of our project is to develop an IoT system that makes significantly better the internal processes of a traditional supermarket. This system allows to provide a higher supermarket efficiency and a better customer experience. The system is based on a microservices-oriented architecture, thus data are exchanged, collected, and managed through Internet. In this picture, we can see the use case of our project. Let's analyze it step by step. The store catalog is the service and device registry system. It registers and provides the resources available in the network exposing JSON-based RESTful API. The store catalog contains entries of everything that is meant to be discovered by applications and other services. The nodes in the network send REST requests to the store catalog, which will give back all the informations needed. The catalog contains all the useful information to make the whole system working: the Telegram token, the ThinkSpeak user API, the Mosquito settings, the list of authenticated employees, and the list of active services. The catalog is reachable through an URL available for every entity in our system. All the services register themselves, sending a post request to the catalog every 5 minutes. When the post request is received, the catalog updates the catalog.json file, adding the service that has sent the request. To keep the system always updated, the catalog make a check every 30 seconds to remove the services that are not updated for more than 10 minutes. 2 checkpoints skipped. For this project we used ThinkSpeak as database. We created 4 channels, one for each category of products in our supermarket. Each channel has 8 fields, corresponding to 8 different products. Since ThinkSpeak is pretty limited as database, we exploited tags and metadata to extend its functionality according to our needs. Metadata contains prices and position of the products inside the store. Tags contains the names of the products. To maintain the scalability of the whole system, we decided to use an adapter. Thanks to this entity, we are able to keep always the same services, even in the event that we decide to change the database, modifying only the adapter's script. This adapter is contacted through GET requests by all microservices that need to communicate with ThinkSpeak and, according to the specific requests, sends back the desired data. It has also an MQTT feature that enables this entity to update data in different ways. We'll see them in detail in the following steps. The reader store keeps track of the products in the supermarket using RFID tags, and updates the ThinkSpeak database through MQTT with the ThinkSpeak adapter. We can see that before the first execution of the reader, all the products have no value in ThinkSpeak. When the reader starts working, it detects all the RFID tags in its range and updates all the values in ThinkSpeak by publishing a message in a specific topic. The ThinkSpeak adapter is a subscriber to this topic, and will convert the message in the ThinkSpeak format. In this case, for simulation purposes only, we initialize them at 20. This entity is always updated on all the products inside the store and, when it detects some changes, publishes an MQTT message to alert all the other entities interested in this event and updates ThinkSpeak. We'll see in the next steps how the graphs follows the trend of all the products. The Telegram bot is the core of our project. It enables all the users to exploit the microservices that we implemented. Starting the bot, the user has to identify himself according to his role, employee or customer. If the user is an employee, he'll have to authenticate himself by inserting a password, given by the company at the moment of the hiring, and stored in the catalog, that will be checked. If it's correct, the employee will be registered in the catalog section dedicated to the employees. Depending on his role, the user will be able to exploit different services. Customers will have a list of functionalities to select. Employees will exploit the benefits of the Employee Alert microservice, which sends an alert to all the employees when products are running out, making them able to restock shelves before they're empty. The Employee Alert is a subscriber to the topic published by the Reader's Store. When the quantity of the products inside the store changes, the Reader's Store publishes an update message that alerts the service of this change. The service contacts the ThinkSpeak adapter, retrieves all the values of the products and, if some product has less than 5 items on the shelf, sends an alert to the Telegram bot of the authenticated employees in order to make them able to restock all the shelves. In this case, for simulation purposes, shelves are always auto-restocked to 20 items per product. Product availability is a microservice that enables the customer to ask for the quantity of a specific product. It's contacted by a GET request sent through the bot. The user inserts the name of the product and his category, given to the service as parameters. If the name of the product doesn't exist in our database, the bot sends an error message. If the request is correct, the service contacts the ThinkSpeak adapter, which will send back the quantity of the desired product. Product position is a microservice that enables the customer to ask for the position inside the store of a specific product. It's contacted by a GET request sent through the bot. The user inserts the name of the product and his category, given to the service as parameters. The service contacts the ThinkSpeak adapter, which will send back its position. Smart Lane is the sensor that enables the supermarket to export all the daily transactions in a database in real time. All these data will be post-analyzed to obtain all the desired statistics. To simulate the real trend of a supermarket, we gave multiple transactions in input to the Smart Lane. In this way, we were able to set some real customer behaviors. When a customer gets through the Smart Lane with his cart, the Smart Lane reads all the products that are crossing the line, obtains the current transaction and computes its total price, according to the actual offers available. All the transactions are published through MQTT, making them available to all the services entities that will want to access to these data. The correlation analysis is a microservice that makes some statistical analysis on the transactions published by the Smart Lane. Every new transaction is added to the transactions record, in order to maintain all the offers always up to date. This microservice analyzes all the transactions and tries to recover some correlation between all the different products contained inside every transaction. Its aim is to obtain custom offers according to customers' behaviors. This service will compute 2 different kinds of offers, single products and coupled products. The discounts on the single products are computed upon the support. The support is the probability that an event occurs. In this case, the probability that a specific product is bought. If this probability is low, we want to increment it by discounting its price, enticing the customer to buy this product. All the products that have a support greater than 0.1 and lower than 0.3 are included in the discount list. We decided to split the discount amount in 3 different stages. Between 0.10 and 0.20, we apply a 30% discount. Between 0.20 and 0.25, a 20% discount. Finally, between 0.25 and 0.30, a 10% discount. In every transaction, it's possible to find some correlation between the purchase of different products by exploiting the association rules. This powerful technique analyzes all the transactions, finding all the products statistically linked together. This concept is based upon the confidence. The confidence is a measure of conditional probability. If a product X is bought, the confidence tells us the probability that another product Y is bought together with the X1. For our project, we chose a confidence value between 60 and 85%. If the confidence is 60%, when product X is purchased, we can say that the purchase of product Y is 60% or more. If the customer buys two products linked together by an offer, he will pay the second one with a 50% discount. In this way, we can apply these correlations to propose custom offers and improve our earnings. This microservice is contacted through GET requests by two entities. The first one is the Telegram bot, in order to communicate to the customers the actual discounts. The Telegram bot sends a GET request to the correlation analysis service, with the offer type requested by the user, given as parameter. When the service receives this request, it computes the correlation analysis in real time. The correlation analysis contacts the ThinkSpeak adapter in order to retrieve all the prices of the products in the store. The correlation analysis service will send back to the bot the discounted products and their discounted prices, computed starting from the base price taken from ThinkSpeak. The other entity that can contact the correlation analysis service is the Smart Lane. It sends a GET request once a day, in order to be always updated and provide new daily discounts. Every time that a cart crosses the line, the Smart Lane applies all the available discounts, obtaining the correct amount for every transaction. The time analysis service is subscribed via MQTT to the Smart Lane topic. Its main functionality is to graph the crowding of the store in all the different moments of the day/week. Every time that a transaction is published by the Smart Lane, the time analysis service stores its timestamp in a database. Every time that this service is contacted through a GET request from the bot, it sends back the needed data to draw a plot bar inside the bot. Noted is a tool that we use to keep track of all the offers, products inside our store and the earnings. It's intended for the store manager. We have three flows, one for the single products discounts, one for the discounted coupled products, and the last one for total earnings. Every flow starts with an inject node. Its task is to trigger a GET request to the catalog, sent by an HTTP request node, in order to retrieve the URL of the check discounts service. This URL is given in input to a Python 3 function node, which adds the desired parameters to the URL itself. The complete URL is given in input to an HTTP request node, which sends the GET request to the specific service. Finally, the data received from the request are given in input to a Python 3 function node, which transform the data in order to plot them through Node-RED tables. Finally, we have a section dedicated to show the live ThinkSpeak graphs of all the products.